All right, well, how y'all doing?
Good.
Good? All right, 4 days of lecture left, that's it. And then we're done. So I have a few handouts for you today. So the first one is going to be, so I just handed back mini exam 6. This is going to be mini exam 7 and 8 if needed. In other words, if you do this, it'll count for 2. Unless you're already happy with the ones you have, I'll only count it once. Or if you've already got 6 that you're happy with, you can just stick with those. Understand? So this is either worth nothing or worth 1 or worth 2 mini exams. And what it is it's last semester's final. So you're going to complete last semester's final, and this will be due the day of the final. Okay, make sense? And I encourage you to ask me for help each other. I don't care. I just want you to know how to do this because your final, I'm not going to say it's going to be exactly like this, but this will give you some idea of what I've asked before in the past. And you'll also notice on these, and I didn't even take the time to like make it a new official. I just printed out the actual final, so it doesn't even say mini exam on it. So what you'll notice in real small print, can you see there below each one? It tells you what section it's from and what number. It's straight out of the ebook. So last semester's final, I took problems directly from the homework, and that's what I put on the final. So you can see here, the first problem is from chapter 11, Lagrange, okay? We didn't have a Lagrange on ours, so we need a Lagrange. And then look at where we go. From there, jump straight to 12.6, and that's going to be a triple integral. And then number 3, now we're in chapter 13, section 2. So what chapter are we in? We're in 13.6 today, right? That's where we are? So number 3, 13.2. Number 4, 13.3. Number 5, 13.4. Number 6, 13.6. So that's from today. Number 7, 13.7. We haven't talked about. Number 8, 13.8. Number 9, 13.9. And that's it. Right? So in theory, you can do the first 5 of these now. In theory, right? We've covered everything through the first 5 problems. All right? So enjoy. Like I said, ask questions if you have them. The most important thing is that you understand how to do the problems. And yeah, any questions? All right. All right, the next thing I have for you, anyone that wasn't here last time that needs the handout on parametric surfaces? We started covering this last time. Come on.
This was Wednesday, right?
Wednesday, yes. Hold on, I have 1, 2, I only have 3. That's it. Hold on, I thought I had more. I printed enough for the whole class. I don't know where. Let me check here. Let me just double check that I don't have them hiding in here. I don't know. All right, I'll get you a copy.
Okay.
I'll get you a copy, sorry. But I also have another handout for you. And this is the handout for 13.7. And it's again in color, it's nice and pretty. And this is a really important handout, it has a bunch of stuff on there. Should be, oh, I think there's more than. All right. You hang back over there, or you good?
No.
Yeah, okay. All right, everyone have one of those?
How are you
Good, good. Yeah, no, oh, wait. Yeah, I'm negative. I've been negative for, I've taken 3 tests. I'm good. I never got it, so my wife did, but. Okay, yeah? Yes.
So you're saying this is going to be, this is our review for a final. But you're saying you're going to count this as your exam fee?
Yes, so the thing that says spring exam, right? That is going to count as mini exam 7 and 8.
Oh, this?
Oh, was that why it's so big?
It's last semester's final. So some people already have 6 grades that they're happy with, so they don't have to do this. But if you have 2 grades that you need, this will count as 2. Or if you have just 1, I'll always do what's best for you, right? Like if you have 5 good grades, you just need a 6th one, I'll count this. That make sense?
Yes, sir.
Okay.
So is it both like the 7th and 8th
Yes.
exam and also a kind of a review?
And a review.
Oh,
Kind of, yeah, it's kind of killing 10 birds with 1 stone.
Is it like the same grade twice, or are there sections that are like?
No, it'll be same grade twice. Yeah, it'll be just duplicated. Yep. And I said that as of right now, under each problem, it shows the section it's from.
Yep.
So you can do the first 5 in theory right now. Yes.
So this is sort of like the full review, or what should we?
The review that I normally have given out is like 10 pages long. So I have another review that I can give you,
Just curious.
you know, that's more in depth than this. But this is what that, you know, I have to pick from a lot. I mean, there's a lot of material, right?
Yeah.
So I have to pick from something. So this gives you some idea of what I picked from in the past.
Oh, I have a question on
Yes.
the final. Are we gonna be able to do a similar thing like for the midterm where we wrote a page, like an 8.5 hour?
Like a reference sheet or something? Yeah, I think we'll do something like that.
Okay.
I'm even open to the idea of just doing like an open note test, you know, but it can only be like your notes and homework or something. I don't know. Let's see when we get to it. All right. Yeah, if you have questions, we can talk after class. So there are a few of you that the parametric handout, this one in color, this one from last time on Wednesday. I don't have enough copies. I don't know why. I thought I brought enough, but you have yours? Okay, so I need 1, 2, at least 2. So I can get it to him after class if you want, or you can email me and I can email it to you. But you know how I am with my emails. A little slow. All right, so what we were doing last class is we were establishing the fact that back in an earlier chapter, chapter 10, section 7, that when we had functions, when we had defined what vector functions were, r of t equals either a 2-dimensional or 3-dimensional vector, that what these basically gave us were curves in 2 or 3-dimensional space. Either a 2-dimensional curve or a 3-dimensional curve. And then we said, okay, well look, we don't want to draw curves now, we want to draw surfaces, and we want to use a parametric vector equation to do it. And so I established in class last time that in order to draw a surface in three-dimensional space, we will need to define a vector function r of uv. So instead of just taking on one variable t, we're going to have 2 variables that we have control over, and then each component of the vector will be determined by some function of u and v, each of those. And so then what I did was I handed out this handout and we started practicing trying to draw some of these surfaces. And that's where I'm going to pick up now. I don't know why I don't have this open. So we did the first one. We came up with the way to draw that surface. And then we did, this one was a pain in the ass, right? Because we had to come up with 4 surfaces, including we had to find the equation of that plane that cuts across the top there. So we had to cross some vectors, and it was pain. And then, did we not do this one? No, right? So does anyone have anything for me today? No? Anyone do that? I offered a little bit of a bonus for anyone who wanted to try any of these. No? No one? Okay, I understand. It's Thanksgiving. Okay, did I do this one then? No? Okay, so let's take a look at this. What we want to do is draw this surface. Well, it's a cylinder, right? Now, we know how to define a cylinder already. There's a simple equation for a cylinder. This one looks like it has a radius of 1, right? It says it up here. Here's the equation of it. X squared plus z squared equals 1. That is obviously the equation of a cylinder. Hopefully I can say obviously and everyone agrees. Right? That's the equation of a cylinder that draws basically unit circles in the xz plane. It goes down the y-axis. But I only want our y to go between 1 and 4. So, I mean, we already have a way of defining it, right? But we want a vector function which draws this for us. And so I'm going to start by writing down r of uv. And it's going to be 3-dimensional. And let's talk about things. I want to draw a bunch of circles, right? I want to draw like a circle here, just a bunch of circles. And all of those circles have to have a radius of 1. And those circles kind of live parallel to the xz plane, which means I need to control the x and the z variable and draw a unit circle. So how can I do that?
Sine and cosine.
Cosine and sine, right? So I'm going to say, I'll put 1 here, I don't need it. 1 cosine variable. U, let's use U. I can use U or V, I'm going to use U. And then 1 sine V, I mean sine U, sorry. And in that case, U would be between 0 and 2 pi. And that will draw me circles of radius 1 in the xz plane, or parallel to the xz plane. Now I need to actually basically draw all the circles that go back and forth, right, with our y going between 1 and 4, right, to create the cylinder. So that means I need to control the y value here. Let's let that be the other variable, v, and then let v go between where?
0 and 4.
1 and 4 in this case, yeah, 1 and 4. Right, yeah, it kind of looks like there's a gap there. See it?
Oh, yeah.
Yeah. Okay. Does that make sense? Circles of radius 1 in the parallel to the xz plane, and then we're just going to move them back and forth with our y coordinate. That's our v, and it goes between 1 and 4. So one thing you could do is you could just imagine right now, if I fix v to be 1, right? If I fix v to be 1, that means our y coordinate's 1. So imagine this was a 1, and then go draw a circle, right? So that would draw that circle back there, right? And then if I let v be 4, I'm going to draw this circle. And then everything in between would draw all the circles in between and create the cylinder. Okay, there it is. That's the vector function. Pretty okay? All right, let's look at the next one. So for this one, find the vector function which yields the red end cap of this. So it's the same picture we just had, the same cylinder we just had, but I only want the red end cap, which is this one right here. This is the red end cap. So I want that instead of the whole cylinder. So for this, what's different? What do you see as like the big difference? Y is 4, right? That's fixed. Y is 4. If I'm drawing this, right? My y is fixed. This is 4, okay? But I have 2 variables I have control over. Do I need both of them?
No.
Do I? Well, I need to be able to draw a circle, don't I? Of what radius?
1.
1 and? So I want the entire cap, don't I? So I want the radius to be 1 and then everything down to a point, right? So I need one variable to draw me circles, cosine and sine, and I need the other variable to adjust its radius. Understand? So I get a disk instead of just a solid circle. So let me see here. I'm going to do cosine u sine u here. That draws me circle. Right now that's a circle of radius 1, isn't it? But I want that radius to adjust. 0, 2 pi here. So I want that radius to adjust. So let me adjust it using the variable v in front. V in front. And then v would be between 0, and 1. See, there's a big difference between drawing a circle and a disk, right? With a disk, you have to be able to shrink it down to a point and then expand it out. In the previous problem, when we were drawing that blue cylinder, our radius was always 1, right? So we didn't need anything in front, and then we used the V to control back and forth so we could draw the actual cylinder. Okay? All right. Just for the sake of doing it, what about this back end cap? What would that back end cap be? Same formula, but 1 right here, right? Okay. So you could, if you looked at this whole object, you could see it as 3 surfaces, right? A back surface, which would be that function with a 1, the red end cap, right, which is that one, and then the blue, which is the one we just did prior to this. You could look at it as 3 different surfaces. All right, let's look at this one. Now on this one, I need to give you some information because it's the same cylinder. Okay, it's the same blue cylinder, but I've moved it a little bit, just so you're clear. I moved it. It's no longer back at y equals 1. It goes all the way to the plane. Do you all see that? Okay, and then I've sliced through it, and I sliced through it with the following. So I'm going to label this for you, and I wish I could give myself some more room here. I guess this will work. So let me label this. You can label yours. This right here is the surface x squared plus z squared is 1. We knew that already. This back end cap is a plane, y equals 0. And then this right here, does it bother you that I didn't do it? Okay, there we go, like that. And then this one is x plus y minus z equals 2. So that's what I would give you, okay? I would give you that, and I'd say, okay, I want all 3 surfaces. I want you to give me the vector equation for all 3 surfaces. So we're going to have 3 different answers. So let's do this one. We'll call this surface 1. We'll call this one surface 2. This one surface 3. All right? So let's go with surface 1 first. Well, I'll do R1 of UV. And isn't that what we just did? Right? It's the one where we want to adjust the radius to create the disk. So V cosine U. Yeah, 0 for y because it was backed up all the way to the xz plane. And then V sine U. There we go. By the way, the book takes absolutely 0 time to go through this. They just assume that you all just can understand this automatically. I always do this as a supplement because if you can't do this, then the rest of it's going to be hard. All right, so got that? S1. S2. We did that already, didn't we? It's kind of, right? There's something different here. There's something very different. It's the cylinder, but it's been cut, right? So how are we going to do this? How are we going to do this? Any ideas? Go ahead.
The x and the z would be the same.
The x and the z are the same as it was earlier. So what? Cosine u?
And
Sine u? By the way, u here is between, I didn't put it here, but u is between 0 and 2 pi, and v was between 0 and 1. Sorry, I should have stated that here. Okay, so do you all agree with this? Does this still draw you circles, radius of what? 1. Circles of radius 1 parallel to the xy plane, right? Now, is that what we want? So if I look at this, if you look at it straight on like this, right? The blue is still circles, right? If you look at it this way, it's still circles. What's different though? They come out, they don't go back and forth between 2 constants anymore, do they? They don't go back and forth between 2 constants. So what do they go back and forth between? How are we going to do this? Yeah, how? Yeah, okay. I want to hear your ideas.
Well, we know that the slice, right,
Yeah, this plane, right? So your y's need to go back and forth between here and here, don't they?
Yeah.
And that varies, right? It depends on where you are. That's dictated by the plane. So what do we want here?
Do we set the parameters not equal to a constant, but?
Yes, you can. You have control. Now this parameter you've already set is between 0 and 2 pi, right?
Yeah.
Okay.
So V is the one component.
So yeah, you want v. You want this to be v, right?
Yeah.
And earlier we just said between what, 1 and 4, but now we don't want it between 1 and 4. We want the v between the backside, which is 0, but what? Out to the what? To the plane. So you have to take this plane equation and solve for y, because the v is our y coordinate, isn't it?
Yeah.
So if we solve this for y, we get what? Y equals 2 minus x plus z, right? Isn't that what we get?
Yeah.
However, what's x for us? Cosine u. And what's z? Sine u. So we want this to be between 0 and 2 minus cosine u plus sine u. Interesting. So let me see if I can convince you that this is going to work. Let's pick a value of u. Okay, I want to fix a value of u. Let's let u be 0. If u is 0, let's see where we are. If u is 0, what's cosine of 0? 1, and sine of 0 is 0. So this is if I let u be 0, that's where I am. And now what would v be? Well, if u is 0, v will be between 0 and 2 minus, what's cosine of 0? 1, and then sine of 0? 0, so 2 minus 1. So between 0 and 1. So this v here is between 0 and 1. So think about where this is. This is x, and this is our x component and our z. So if we go out here, right there to that, that's like 1 and then not going up, right? My y is supposed to go between what? Right there, back and forth between 0 and 1. Okay? Now, where do we have it? Where would it be the biggest? Looks like maybe over here somewhere, right? Let me kind of rotate around. Maybe we can tell by looking. Ooh, it looks like it happens. I don't know, what's that angle? We have to look at it from the backside, where x and, because this is the x positive and z positive. What angle does that look like? It was over here, right? What is that right there? 3 pi over 4? So if I try u is 3 pi over 4, right, then where would we be? So what is cosine of 3 pi over 4? Negative root 2 over 2. And then sine would be positive root 2 over 2. So that basically puts me right there. And then my y is going back and forth like this, right? So my y is going to go between 0 and, my y is my v, right? Is between, let's see, 2 minus, so plus that, right? And then plus that. And that's as big as it's ever going to get right there. And so I'm going back and forth between that. And so let me spin this just this way. You can see that's like from here all the way between here and here, back and forth. Just trying to convince you that this is doing what we think it's going to do. So our answer is this. Our answer is that right there for S2. All right, let's try S3. So for S3, we want this one right here, right? This reddish one, which if you look at it from straight on, that looks like a what? The red part looks, from straight on, it looks like a what? A disc. It's a disc, right? It's everything inside. We know how to do that, don't we? Okay, so for S3, R3 of UV. Okay, how did we do disk? Disk, we went V cosine U, V sine U. And then the V, the U's between 0 and 2 pi, and then the V was between 0 and 1. We've used up all our variables, right? And we've used up our restrictions, which means this right here, tell me about the y coordinate. Yeah, it's like the endpoint. So it's the plane itself, isn't it? It's the plane. So it's that solved for y, which I did a second ago. When I solved that for y, what did I get? 2 minus x plus y? Oh, no, plus z, sorry. Plus z. But now for us, what's x? This, and what's v? Z, this. You see? So this right here, I'm not going to have space to write in here, I'll try. 2 minus v cosine u plus v sine u. See the difference between that? Those two? Here, our y coordinate varied, right? Because we want to draw everything along this cylinder. So our y coordinate needed to vary, right? Here, our y coordinate is always on that plane, which is always on that disk. So we have to draw the disk first and then adjust this. I hope that that makes sense. All right, let's do another one.
So pretty much the last section of the vectors always be in respect to whatever we designate at the beginning?
Yes.
Okay.
Yeah, if the one you are still trying to solve for, if you've used up all your variables, right, like we had, like we can't do anything else. We don't have like u, v, and some other variable. Then this has to be based off of whatever you have, right? Has to be based off that equation, has to be solved for that variable, y in this case, and then the x and the z have to be in terms of what you've said x and z are for you in this, the component functions, right? Okay. All right, let's look at this one. I need to tell you what that is first. It's like a little dome. Let me kind of spin it around so you can see it a little bit. Just a little dome here. See it? Okay, and I'm going to give you the equations of these things. So of course the bottom of this thing is just z equals 0. And this top surface here is z equals 1 minus x squared minus y squared. So like a little paraboloid. How many surfaces do we have? 2, right? So let's come up with equations for them. Let's call this one S1, this one S2. Start with S1 because it's a little easier, I think. S1, R1 of UV. What can you tell me for sure? Z is 0. Okay. And then can you tell from the picture what's going on here? It's a disk. It's a disk of radius 1. Now, if you couldn't tell from the picture that that's radius 1, how could you determine it's radius 1? You could figure out where this hits the ground, right? And if you set this equal to 0, right? The ground means z is 0. Set that to 0, move the x squared, y squared to this side, and you get x squared plus y squared equals 1, which is circle of radius 1. But I'm just going to go off of that. We already kind of see that. And so I need to draw in the x, y plane, I need to draw a, not circle, a disk, right? I can do disks. V cosine u, v sine u. U's between 0 2 pi. V's between 0 and 1. There we go. That's my disk on the ground. Questions? Now S2, this is the interesting one, because S2 is essentially the same disk, except that your Z is like you're pulling it up, right? You're like pulling that disk up and creating this like bulge out of it, right? So I still need to draw a disk, right? If I look at this from the top, the blue looks like like the same disk I just drew. So I'm going to put that same formula here, V cosine U, V sine U, right? But this is no longer 0. This is actually, and you've used up your variables, right? It's still the same restrictions. 0 to pi, 0 to 1. So the only thing that can be is what? Yeah, the Z equation, right? Solve for Z, which it already is. That, but replacing your X and Y, right? Let me do that over here. This would become Z is equal to 1 minus, let's see, what would it be for us? V squared cosine squared U minus V squared sine squared U. And you could factor out a negative V squared, and then you get cosine squared U plus sine squared U, which is just 1, so you get 1 minus V squared. There it is. Now you could have just written this whole thing in there, right? You could have, but that's just cleaner. Now, let me grab, can I have one of these chairs? Is this one all right?
Yeah.
Okay. We haven't done this ourselves. So like when I did these, right, when I made these notes and stuff, I did it in Mathematica, Wolfram Mathematica. So, you know, I put in all the code to do it. But nowadays, right, we just go to, let's try this Desmos 3D. I don't even know how to do vector equations. So let me try something. Parenthesis, t, comma, t, comma, t. Yeah, I drew a line. Okay, so that's good. Let me try V cosine U V sine U. Oh, it's doing something. 1 minus V squared. What am I missing here? Oh, yeah, it's not. I'm just curious how to type this in, surface of